Hello learners, welcome to NeenvIAS. This is our concept classes, and today in science and technology we are going to understand what is quantum computing, right? So behind me is the image of the quantum computer. Now we'll see why it is shaped like that later, right? So to begin with, I want to share a quote by Mr. Richard Feynman with you, right? He said, if you think you understand quantum mechanics, you don't understand quantum mechanics. Now, at his time, things were very complicated and we were just beginning to understand what it is. Right now, we have a better picture, but let's say not the complete picture, but still we have better understanding of what is quantum mechanics, right? So why I shared this with you? Because things are going to get confusing, right? But then again, I have constructed this in a manner that for UPSC, we can understand the basic concepts in a simple manner without using too much jargon. So before understanding the word quantum and quantum computing, we should understand what is classical mechanics or classical theory only briefly, because the classical things we are using right now. Okay, the classical things we use right now, as you can see on the board. So the first one is classical mechanics. Now this is the mechanics that we observe in our daily life. We observe in our daily life, like a car accelerating or a car braking, right? A person running, a person stopping. If you don't pay attention on the road, you hit someone and there is momentum clash and then somebody gets hurt. So all those are mechanics that are because of Newton's laws. Okay. So this is the classical mechanics that we see in everyday life. We don't need to go into more depth. Only thing we need to understand that this is predictable. Like we know if we are going from A to point B, we are at least going to end up there if everything goes right, right? So there is a predictability. But why am I telling you this? Because this is obviously a very common phenomena. You observe something, you throw a ball at your friend. If you're doing it right, it will go towards them, right? If a person hits a six, it is going outside the boundary. So we'll understand why am I telling you this when we understand quantum theory. So what are classical computers? We're going this way. First we see the mechanics, then we see the computers, and then bits. So first thing is classical mechanics that we observe in our daily life. So what are classical computers? These are computers which are based on the rules set by classical computing. Okay, they work on the basis of classical mechanics. That's all we need to know. Now this is the important point which we need to understand. Imagine a house. Now the basic building block of the house is a brick. Similarly, basic building block of a classical computer in terms of information is a bit. So in a house there is a brick. In a computer it is bit. Now it is the piece, or let's say the house of information storage. It is a binary language. That means bits are either 0 or 1 or 0, and here or is there. It can't be both, right? So if we imagine binary language as switch, so off will be 0 and 1 will be the on switch. So like a normal switch in our daily life, right? Because it is based on classical mechanics, the normal switch is either on or off. So bit is either on or off, it is 1 or 0. So if we want to write A in a bit language, it will look like this. And if we want to write B, it will look like this. So just to explain you a little bit, if you imagine, let's say you are sitting on a laptop or a whatever, or a keyboard or whatever, wherever device where you are typing A, B, C, D. If you type A, you look at the keyboard, and either it is a physical or a virtual keyboard, doesn't matter. You are typing A. A is part of English. You will see English, but the computer will understand 0, 1, 4 zeros, sorry, 3 and 5 zeros and 1. So A will be interpreted in binary language by the computer because it does not understand English, right? So this is why I've told you about bits. Next, we'll come to quantum concepts. We have seen classical mechanics, classical computing, classical bit, but now we will see quantum. Now, quantum physics, quantum theory, and quantum mechanics, they are same for us in terms of UPSC. Although if you want to differentiate, quantum mechanics is the mathematics of quantum physics. Whenever there are formulas or calculations involved, it becomes mechanics, right? Okay, so I have explained this. So basically in quantum theory or quantum physics, we deal with smaller particles like atomic, subatomic particles like proton, neutrons, electrons, like this. Okay, and in classical mechanics, we deal with things bigger than that, right? We deal with chair, table, camera, this pen, but I'm not dealing with atomic level, individual atoms, individual electrons right now. I'm dealing with collection of atoms, correct? So this is the difference. So quantum mechanics has some features. See, first thing is it is unpredictable. I told you in the previous slide that classical mechanics is predictable. NASA, when it sends a spacecraft into an orbit, it knows how to send it because of classical mechanics. Path is predictable. But in quantum world, path is not predictable. In quantum world, if somebody is traveling, it is a probability that they will exist in an area. And when you observe them, then you will see where they are. But in classical mechanics, let's say you're sending a spaceship, you can have a camera on Earth and track it everywhere. And it is being done right now. You can track airplanes also. And that is the application of classical mechanics. That means the rules. But in quantum mechanics, you cannot pinpoint a location every time. Whenever you observe something, right, then you can see that something is there. But when you're not observing, when it is in a quantum state, it will be a different thing. Don't worry, it is confusing, I know, but I have simplification for you coming your way. But before that, I wanted to introduce this statement to you that when you observe something which is in a quantum state, then it becomes in a classical state. Very confusing, I know, but don't worry, I have the explanation for you. So probability is used rather than accurate fixed point of the particle in a quantum world. Don't worry, we'll understand everything. So the quantum mechanics, it was developed by a lot of scientists like Max Planck, Albert Einstein, Niels Bohr, Erwin Schrödinger. Now they discovered that at very small scales, at atomic scales, particles don't behave like big objects as we see in the world, right? They have very different rules. They are just totally different rules in quantum world, right? So they have their own special rules. For example, science fiction movie Ant-Man Quantumania, they had this world, quantum world, although what they have shown is not scientifically accurate, but yes, it is shown that they downsize to, you know, subatomic level, then they are seeing germs and all that. So that is true, that part is true. And there is also a scene in which lot of probability is shown. There are a lot of Ant-Man characters are there, lot of them, and probability is there. So that is also correct depiction that probability exists. Like there will be a lot of Ant-Man, and when you observe them, when you see them, then it will be one Ant-Man, right? So what is the meaning of the word quantum? The quantum word means smallest part of something. For example, in economics, you must have heard this term, quantum of funds is given, right? So quantum of funds, collection of funds is given. So quantum means one part, and multiple of this word is quanta, right? So in the house, in a physical house, the smallest quantum of house is a brick. I hope now you get it. So what is the quantum of light? It is photon. What is quantum of electricity? It is electron, right? So this is how you can understand one photon, one electron is quantum of light and electricity respectively. Let's move ahead. What is quantum computing? Now, of course, many people, many books, many teachers, you will find discussing the first definition, which is also correct. I'm not saying it's wrong. Quantum computing is an area of computer science that uses principles of quantum theory. But I've got a better definition for you, which you will get in our sessions also. I try to, let's say, differentiate your content. That is one of my aims while creating the content for my classes, that I differentiate the content from what is available so that you get you get a different perspective, and UPSC cannot fool you. So quantum computing uses laws of quantum mechanics. We are same almost till here. Now to solve the problems of which are too complex for classical computers. Now this is a better definition. It gives you a comparison also and gives you the source of laws also, right? So try to use this one. All right. So let's continue with the concepts. What is quantization? Now it means that some properties can only come in specific amounts. Okay, like quanta. We have discussed quanta, right? For example, you only can have rupee 1 or rupee 2, rupee 3. You cannot have 2.5 rupees. Although we have 2.5, we can 2 rupee and 50 paisa. But in quantum mechanics, you cannot have 2.5. Another example which you can have is, let's say you are going from 3rd floor to 4th floor. You cannot be in between the floors, right? So let's say this is the 3rd floor, this is the 4th floor, and there are stairs, right? Excuse my modern art. So this is the 3rd floor, this is the 4th floor. You grow from 3rd to 4th, but you will not exist here. You will either exist at 3 or 4 in quantum world, right? Observation and measurement. Now this is what I was talking about, which is very confusing. Now see, let's say a particle is in a quantum state. It is in a quantum state. Now that state is called superposition or entanglement. It doesn't matter right now. So it is in a quantum state, and at that time you cannot observe it because it exists in a probability. I have told you. Now when you observe it, when you try to find it, then it will become stable at a place. And when something is stable at a pace, when it is predictable, it becomes classical. So this is how, after observation, the quantum state falls and it turns into a classical state. So for example, let's say in quantum physics, observing a particle can change its behavior. For example, when you toss a coin and you cannot see when it is revolving, you don't know what will come when it is spinning, right? Head or tail. It goes till here, it comes back, you catch it, and then you see, okay, heads or tails. So if you don't look at a coin, it can be both heads and tails at the same time, but moment you look, it turns into classical. That means it is predictable, right? This is because act of measurement changes the state of particle. Now please don't try to imagine it, because this does not exist in our life usually. This exists in nature, but it does not exist in our life. We cannot visualize it. It's a little abstract. So try to just understand what I'm saying by examples. Remember the examples. Wherever difficulty is there, I've got ample examples. So what is a qubit? We had discussed a bit, and by comparison, let's quickly understand qubit. It will be easier for us. So what is a fundamental unit of information in quantum computing? It is qubit. I am not explaining this because we have already discussed bit. So it is similar to bit, but it has a twist. What is the twist? See, in classical computing, the bit can be either 0 or 1, but in quantum computing, qubit can be 0 and 1. Okay, 0 and 1. I'll show you how. We'll have another diagram. So qubit can exist in a superposition. We'll see what is superposition. That superposition basically means it has it can have two states. That means it can have 0 and 1 simultaneously until observed. I've told you that observation breaks the quantum state. So what will be the light switch? Think. Here light switch will be either on or off. Here it will be both. But once you go and look at the switch, it turns to 0 or 1. But until you are not looking, it will be 0 and 1, right? So after observation, it becomes a classical bit, but between observations, it is a quantum bit. Here, I think this will make things better. Bit 1 is 0, bit 2 is 1, but qubit can be 0 and 1. Some part of it will be filled, some is blank. So 1/3 is 0, 2/3 is 1. So this is how a qubit can look. This is just a visual representation to explain. Let's say there are 20 red balls, 20 blue balls. Here it can be a mixture. So 8 out of 20 are 0, 12 out of 20 are 1, right? Now what is superposition, which I just mentioned? It means both at once. Let us see the definition. Superposition is a quantum principle that refers to a system existing in multiple states at the same time. Now this is a very fancy way of saying that it can do two things at once. Let us see an example. Let's say I am spinning at this side and then I spin at this side. In our classical life, classical mechanics, we can do it only one side at once. But in quantum mechanics, if I was in a quantum state, superposition state, I could do both at the same time, right? So it's so weird. It's so different from what we see in our real life. So a system in a superposition may exist in combination of all possible stages until it is measured. So if I spin and somebody comes and sees me, if I'm alone in a superposition state, I can spin in any direction all the time, in all the directions all the time rather. But if somebody comes right now, let's say the studio is closed right now, somebody comes and looks at me, then of course I am standing or in a classical state. But if somebody is not observing, I am in a quantum state, in quantum world. One example in real life which we can see is that sunlight, when it is white, it is just one color that we see. But when it is going through a prism, we can see that it breaks into 7 colors, right? So 7 colors are superimposed and made into a one particular color, right? So this is the example of superposition having multiple states. So a coin toss, if you toss a coin, when it is not being observed, it is in a quantum state. We can take it as an example, okay? And when you observe it, then it is in a classical state. So superposition gives quantum computers superior computing power. Why? Because a bit can be 0 or 1, but quantum bit can be 0 and 1. So it can, one quantum bit can perform more calculations than a classical bit. This is why. So basically the quantum computer will have different parts which will give it power to do more calculations than normal computer, right? For example, cryptography. Right now, cryptography means hiding your messages. Cryptography right now is relying on mathematics. Harder the encryption, that is, if you want to hide your data better, you need to use more mathematics. And supercomputers can crack it. But quantum computing can crack it like this. Supercomputers might take some time, but quantum computing can break current encryption like this within few minutes. So quantum computers utilize superposition and other quantum properties like entanglement, but mostly superposition. This can potentially break these encryptions quickly. So we need new cryptography, and research is going on. Like quantum satellite has been developed by China for testing this quantum cryptography. Right. So let us see this image in which there is a ripple by this drop. Okay, it is going out, and there is a ripple by another drop. It is coming inside. So waves are coming here and waves are going there. At this point they are meeting. So at this point somewhere they are meeting, right? So they will superimpose. That means at this point two waves are existing at once. So this is how you can imagine. To understand this, since we cannot see this quantum effects in real life, we need to understand by such images and visualizations, right? Another example that the scientist Erwin Schrödinger gave, he explained superposition by this. It is famously called as Schrödinger's cat. So he said that, let's say in a box there is a cat and there is poison, right? And then you put the, well, of course you put the poison, you put the cat, and you close the box. Now when you are not observing the box, the cat is in a quantum state. That is a superposition. I mean, it is not going into superposition. This is to explain. So in superposition, two states at once happen. So cat is alive or dead until you observe the cat. That means box is lying, you don't know what is happening, cat is silent, nothing, no noise. So you don't know if the cat has eaten the poison or not. So if you observe, you open the box, then you will see, okay, either it is alive or dead, right? So when you observe, quantum state breaks and it leads to one of the states. I hope you understand this, right? Final example, a final diagram in the sense for this part. Classical bit will be 0, 0 or 1. Okay. Now quantum bit, it will exist in a probability in this, like it can be here, it can be here, it can be here, it will go everywhere. But when you measure it, it will be at one place only, right? So when you measure it, right, then it goes to either 0 or 1. So because of this property of multiple states in the quantum bit, you can have parallel computations. Exponential calculations will happen once you increase the qubits, and massive amount of data can be handled, right? So bit versus qubit, and there are two diagrams. What do they say? See, superposition helps in exploring multiple paths at once. In qubit, the qubit will go, right, whenever it let's say, oh sorry, this is bit and this is qubit. So in qubit, wherever it will go and encounter a problem, it will distribute itself, one here and one there. But a bit will go to one path only because it exists in only one state. But qubit can go to multiple paths, right? So I hope with this you can understand the functioning, how they're different. Now we come to the next topic, which is quantum entanglement. Einstein called this quantum entanglement as spooky action at a distance. We'll see why. See, entanglement means like the cat was entangled in a wool yarn. Similarly, entanglement means two particles, subatomic particles, are joined together. Okay, two or more quantum particles are linked together. They are linked in such a way that their own identity is replaced with a combined identity, right? They don't have their own property now. Let's say there are two best friends, right? If something happens, the other one knows, like this, something like this. Or let's say twins who are deeply psychically connected. So if something happens to the one twin, it will inform the other twin. They'll get a feeling. So they are interconnected. When one member is measured, you can know about the other member. That means you don't need to measure both to understand what the system is doing. Very clever. For example, like twins and two friends, which I've just discussed. Okay. Now, recently there has been a news, right? Sorry, it was in 2013. So quantum spooky action travels at least 10,000 times faster than light. So this was discovered in 2013, right? So again, why am I mentioning this? Because UPSC can just insert somewhere in some exam, let's say UPSC, CDS, whatever. So they can, civil services or CDS, they can just ask if it is faster than light. So yeah, it is. Entanglement is faster. So what happens is, I'll tell you where the faster than light part comes. See, if you measure a pair of entangled protons, first you entangle them. Okay, by scientifically through various devices, you entangle them. There is one, there is two. These two particles are entangled. That means, let's say, if first is red, it is measured and it is red. Second must be blue, because this system is of color red and blue only. And if you measure one, it is blue, second must be red. So this is entanglement. It is very easy. But the point is, this will work even from one end of the earth to another. That means distance can be a lot. If you have heard about Three Body Problem TV series, there they have used this concept of entanglement. And in their story, it is working light years away, let's say 400 years away. Okay, so this is the thing. So what are the applications that has, this led to? See, MRI scanners, they use magnetic fields of atoms in our body, right? And then they detect the body parts. Lasers work on quantum computing because they stimulate atoms, directly the atoms, to emit light of a particular wavelength. Solar cells, electron microscopes, atomic clocks, they all use the quantum computing principle to work, right? So this is how a quantum computer looks, right? So this is Google's computer, and all these things are basically for cooling the quantum computer, because quantum computer needs a proper temperature, otherwise it will fall into decoherence, which we'll see. So what are the issues? First is decoherence. That means coherence means it is in a stable state. Decoherence means unstable state. So let's imagine, like I'm trying to balance this pen on my finger, right? Let's say I balance this somehow. So if a wind comes, like a gush of wind, or even I do this will fall. So if it is stable on my finger, it is in a coherence. If it falls, it is in decoherence. So quantum decoherence is loss of quantum behavior, like superposition, when a system interacts with its environment. So it causes the quantum state to transition into classical state. So after observing also, quantum becomes classical. Because of disturbance of the environment also, quantum becomes classical state. Okay. So quantum bits are like balancing a pencil. I've given you this example. So slightest disturbance can make the quantum, that is qubit, lose its special quality of superposition. So what is the problem? Now this is very sensitive. Quantum computers are very sensitive to disturbance. A small disturbance can change the whole calculation and it will ruin the calculation. Okay. So qubits need to stay balanced long enough to finish the calculation. Otherwise, you have to start again. So scientists are working on better materials that are more stable. For example, better pencils, or let's say better environment, so that no wind is coming. Error correction codes are being developed that can notice the error and correct it in the calculation. Next issue is quantum error correction. Now this is because I just told you decoherence happens, calculation error happens, and it is very costly to run a quantum computer. So we have to be careful that we need to develop algorithms that can check what the error is happening, what kind of error is happening. So it is essential for development of reliable computers, quantum computers, because quantum states are very fragile. So what is the method? See, external influences are insulated. Sorry, the device itself is insulated from external behaviors. Okay, because a single error, like I said, can cause the entire computation to collapse. Right now, the error correcting methods that are being used, they don't work for qubits because bits are different than qubits. Also, third issue is scalability. That means, let's say in computers right now, in classical computers or supercomputers, you can add more hard disk, you can add more CPU, GPU, RAM to increase the capacity. But same thing cannot be done here, because qubits are unstable by, they're made unstable by the environment. They are very sensitive. So when you try to basically, let's say, see, in normal calculation, every qubit interacts with other qubit. So when you try to create a bigger computer, right, it will be more prone to error. That is why you can't scale it easily like the classical computers. So every qubit must interact with every other qubit, which becomes challenging as number of qubit grows, and since they are very sensitive, small thing can disrupt the whole system. So current efforts like IBM are designing systems to maintain qubit quality as the system scales. Research is going on. Okay, it's a developing frontier technology. Lastly, measurement difficulties. We cannot observe or measure a quantum particle, as you know, if it is in superposition state, because if you observe, then it is no more in a superposition state, and only in superposition state you can calculate something. But researchers must find a way to read the quantum state indirectly without disturbing the quantum state. Otherwise, you will not be able to calculate the output. Right? Now let's come to the next term called quantum supremacy. Now supremacy means, let's say humans are superior to animals, let's say. So we are having supremacy over them. So supremacy means you are higher. So Google has claimed first quantum supremacy in 2019. Now what does this mean is, quantum computer solves a problem that will take classical computer a very long time, which is not practical. That means quantum computer will solve a problem in, let's say, 100 days, but same problem will be solved by classical computer in, let's say, 10,000 or let's say 1,000 years. Now this time is not practical, of course. So quantum computers are super to quantum classical computing, obviously, And Google has published a random supremacy claim in 2019 that they have made a computer that can do this already. In 2022, Nobel Prize was given to these three scientists, right? And Mr. Elaine Aspect, John F. Clauser, and Anton Zeilinger. What they did was they proved that entanglement works, right? So for quantum computing, they were given the Nobel Prize. Let's see some news. See, in 2023, record-breaking quantum computer has more than now 1000 qubits. IBM had 433 qubit computer before this. Now there is a company which has more than 1000. Okay. All right. So that is all for this concept session. There are a lot of concepts to be discussed in quantum computing. We can discuss, and we will surely discuss them later. Right. So that is all for this session. Thank you so much. Thank you for listening. If there is anything, please do let us know. Right. Thank you. Take care.